Now, all unit log have been leading up to this definition for the inverse of the exponential. We've kind of already talked about what it is. That's going to be a logarithm. But let's walk through that now, and then we're going to start to see what the implications of that are. So we've defined previously that an exponential function is a function of the form f of x equals b to the x. And we had a couple other requirements on here. If you remember, we said that b had to be positive and b couldn't equal 1. So we're keeping with this definition as well. Now, suppose I said, let's find the inverse. So we already saw that this is a one-to-one function because it's either always increasing or always decreasing. So we can find an inverse. So if we are to find an inverse, then we replace the f of x with y, giving us y equals b to the x. And then to actually find the inverse, we'd flip-flop the x and y. So remember, that's how we find inverses. We flip-flop the x and y, and then we solve for y. So to flip-flop the x and y, we get x equals b to the y. And now we try to solve for y, but that's the problem. How do I get the y out of the exponent? Well, I don't really have a way. That is the definition of a logarithm. The logarithm is our way of getting something out of the exponent. It's to undo an exponential. So we're going to define a logarithm to be exactly what we want. So what we want to notice here is that what we have in this highlighted area, that is in fact the inverse of the exponential function. We flip-flop the x and y. That is by definition the inverse, but it's not written in function notation. We can't write it as y equals. So what we're going to do is we're going to define a function, and we define the logarithm so that it's equivalent to that. To say, yeah, it means the same thing, but I can write it as a function. I can write it y equals. Now, as you're looking at this definition of logarithm over here, log base b of x is how we read that. Again, log base b of x. So I want to point out that x is what you're plugging into the logarithm function. The base of b is a little bit lower than the letters log there. That's really important that we understand what's being written and what this is. So log base b is the inverse of a base b exponential. So for instance, if I had log base 2 of x, that would be the inverse of 2 to the x. So we could have a variety of different logarithms. We could have log base 3 of x. A base 3 logarithm undoes a base 3 exponential. Now, the other part I want to talk about here in this intro before we get into the specifics is something that I'm going to talk about over and over and over again. And that's going to be this statement here, because one of the things that we're going to want to be able to do is we're going to want to be able to say, how do I go from one to the other? And that's one of the things that we're going to work on here in this lesson is how do I go from one to the other? How do I go from an exponential to a log or from a log to an exponential? So, in order to go in this direction, to go from a log to an exponential, we take the base of the log, which is b, so we take that, we raise it to the power that's on the opposite side of the log, so we're going to raise it to that power, and that's going to equal the argument of the log. So the argument of the log is what we're plugging into the logarithm. So x is what we're plugging into the logarithm. The logarithm in question is log base b. So kind of like how with roots, we can't just say take the root. We have to say the square root or the cube root or the fourth root to define what root it is that we're talking about. So there was an index attached to every root that we ever talked about. Logarithms are similar. We can't simply say take the logarithm. We have to say which logarithm. Is it a base 2, a base 3, a base 4 logarithm? Kind of the same way that you have a square root, a cube root, a fourth root. So we talk about log base b is the function. The input to that function is x. The output is y. And if we want to rewrite that without a logarithm, we take the base of that logarithm, we raise it to the power of the opposite side, and that's going to be equal to the argument. That's the definition of what a logarithm is. It's how we can take a logarithm and rewrite it as an exponential. So let's take that statement that said, take the base, raised to the power of the opposite side equals the argument, and let's apply that now. So I want you to notice what the directions to this problem state, though, so we know when we want to do this. The directions say write the equation in exponential form. So what we're doing here is we're taking a completely true statement and we're rewriting it as a completely true statement that just has exponents in it. So I really want to point that out. These are what I like to call jumping jack problems. If you think about what a jumping jack is, you spread your legs out, you raise your hands up and touch them, and then you get back to where you started. The actual action of doing that is kind of stupid. You're not really achieving anything, but the process of doing it is what's important. You can use jumping jacks as a warm-up before a workout to get your body temperature stepped up, to get your heart rate going, and even stretch yourself out a little bit. You can also use a jumping jack as a cardiovascular exercise to, again, get your heart moving, and if you do a lot of them, you do them with intention, then that's going to be a good exercise. But the end result is nothing. You just get back to where you started. And that's kind of what's going on here. We're going to take a completely true statement and end up with a completely true statement, but the purpose of this is going through the motions to get yourself used to using this rule. So the rule again was to take the base. The base of my first thing here is 5. We're going to raise that to the power of the opposite side. The opposite side is 2. So we're going to raise it to the power of 2, and that's going to be equal to my argument, which is 25. Now, the reason I like to start off doing these types of problems is because we can very easily check our answer by saying, is that a true statement? We started off with a true statement, so we should probably end with a true statement. And so sure enough, 5 squared really does equal 25. We don't want to simplify this at all because that was the whole purpose, was to write this as an exponent. So even though we could simplify the left-hand side to 25, that's not helpful. We wanted to write this as an exponent. So similarly for our second problem, we're going to take the base. That's 6. We're going to raise it to the power of the opposite side. We're going to raise it to the -1. And that's going to equal our argument, which was the 1/6. Again, the argument is what we're taking the logarithm of. And when I have 6 to the negative first equals 1/6, I can again say, does this make sense? Is this a true statement? And yes it is. Negative first power means take the reciprocal. Now to wrap this up, the last one, we take the base. The base is 2. We raise it to the power of the opposite side, which is 1/2. And that should be equal to the argument, which in this case is √2. And once again, we can say, is 2 to the 1/2 power really the square root of 2? And yes, that's the definition of the 1/2 power. So that does work out. All right, so let's go ahead and start to look at what the implications are of the logarithm and the exponential being inverses of one another. So if we go back to what we learned about inverses, we know that when we apply a function and an inverse to each other, when we do a composition of them, we get back to where we started. So if you remember in our lesson about inverses, that's where we said if I start with x, if I apply a function and get some answer, then the inverse just takes me back to where I started. And really, we said the other thing as well. We said if you start with some value, apply the inverse, and then apply the function, you also get back to where you started. So in fancy terms, we can say f of f inverse of x equals x. It means if we plug x in, we do the inverse, then the function, we get back to where we started. So what this tells us is that if we start with the b to the x, and then we apply the logarithm base b, and this is important that they're both the same base to each other, we get back to where we started at x. And so what you can kind of think of this as is you can think about these two things as undoing one another. Now, we're not going to use that swear word cancel because cancel can mean way too many things, but we can see they undo each other because they are inverse functions of one another. Now, this does give us one other thing as well. This does tell us that if we had b raised to the log base b of x, that would also get us x. We use that much less frequently. But what do we have written down here? Log base b of b to the x, getting us just x, getting us just that exponent that was up there, the rest of it undoing each other. That's something that we're going to use very often. Let's look at an example of using it. So what we just saw is we saw that if I have log base b of b to the x, that the log base b and the b to a power undo one another, leaving just the exponent. So if you're asked to find the value of a logarithmic expression like the ones that we have here, what you'd like to have happen is you'd like to be able to rewrite them as log base something and something to a power, where the base of the logarithm and the base of the exponential are the same. And I'm going to repeat that because you might want to jot that down in your notes. What we're trying to write this as log of something and then exponential of something, where the base of the log and the base of the exponential are the same. So in this first example that I have log base 4, I'd like to rewrite 16 as an exponential whose base is 4. And I can do that. I can rewrite 16 as 4 to the second power, or 4 squared. In doing so, I now have log base 4 and 4 to a power. The log base 4 and the 4 to a power undo one another because they're inverses, and all I'm left with is 2. So log base 4 of 16 is equal or equivalent to 2. Now as we move on to the second example here, log base 10 of 1/10, we want to try to do the same thing. It gets a little bit trickier here. We want to try to rewrite this as 10 to some power. And so the question is, how do I rewrite 1/10 as 10 to a power? And what should jump out at you is when we have fractions, when we have reciprocals, we should think about the fact that it's going to be negative. So this is going to be -1 because it's the reciprocal of 10. At which point we have log base 10 and we have a base 10 exponential. So the log base 10 and the 10 to a power undo one another, leaving just the -1. Let's step it up in difficulty one more notch. For this third one here, we do want to do the same idea. We want to say we got a base 9 log. So let's try to rewrite this as 9 to some power. So how do we rewrite 3 as 9 to a power? Now one of the errors that I see people make, so don't write this down, I'm about to show you an error. One of the errors I see people make is to say 3 is 1/3 of 9. So they put a 1/3 there. But remember that 1/3 means the cube root. The cube root of 9 doesn't get us 3. But that actually should give us a big clue that says, oh, hold on a second. Radicals maybe are a good way to go, because the square root of 9 would give me 3. So how do I write square root as a power? The 1/2 power. So the square root of 9 really would give me 3. So this is a valid way of rewriting 3 is as 9 to the 1/2 power, at which point our log base 9 and our 9 to a power undo one another, leaving us with just 1/2. Now there is one other tricky one that I didn't write down. Let's go ahead and talk about though, and we've kind of addressed this before, but let's go ahead and talk about it. What if I had log base 5 of 1? Well, the goal here is to rewrite this as 5 to some power. And so I got to say 5 to what power equals 1. How can I rewrite 1 as 5 to a power? And the big thing you got to remember is that anything to the 0 power is 1. At which point my log base 5 and my 5 to a power undo one another, leaving me with just 0. So this next example, we're told to write the equation in logarithmic form. Now, here's where I want to show you how to go through this problem in what's a method that will help you later. Because one way that you could go through this problem would be to just look back at our definition of the logarithm and try to play a matching game and say, let me figure out what the b is, what the x is, what the y is, and just plug it into this definition over here. And while we could definitely do that, that's not going to be helpful. And these are a second version of what I'd earlier called jumping jack problems, where the whole point of these problems is the process, it's not the answer. Because if we look at what we're starting with, we're not solving anything. We're given a completely true statement. 9 cubed really is 729. There is no ifs, ands, or buts about it. It's a true statement. So we're not solving anything. We're just trying to rewrite this with a logarithm involved. So the point of this problem is actually to work out how do logarithms work, to figure this out and to get a feel for it. So what I'm going to do first is I'm actually going to rewrite this with a little bit of space in here. We'll put a little bar here so we can separate each of these examples. If I want to introduce a logarithm, the logarithm is meant to undo the exponential. So I got to look at the exponential that's in this problem. The exponential is that I have 9 raised to a power. That means the base of the exponential that's in the problem is 9. So if I want to introduce a logarithm into this problem, the logarithm that makes the most sense to introduce is a base 9 logarithm. So what I'd like to do if I'm going to introduce a logarithm into this problem is I want to undo the base 9 exponential by applying a log base 9 logarithm to both sides. Now it's important that we're putting this on the left because we're plugging 9 cubed into the logarithm. We're plugging 729 into the logarithm. So we're taking log base 9 of both sides. Now as we write this logarithm, I want to point out that the log and the 9 cubed are on the same level, the same line. Like if you had line paper here, they would be right on the same line. The base 9 to the logarithm is written a little bit lower than that. That's how we know that this is a base 9 logarithm. It's written a little bit low. It's what we call a subscript. Now, back to this problem. Now we can simplify this a little bit. Because now I have log base 9 of 9 to a power. Those things undo each other, leaving just the 3. Now on this other side, I'm happy leaving it the way that it is because my goal of this problem was to turn this into a logarithmic equation, which now we have. So our goal is to get a logarithmic equation from an exponential. Let's undo the exponential by applying the appropriate logarithm. So moving on to the second part of this example, I'm again going to leave myself space to write the logarithm. Now, as far as which logarithm to write, I look at what the base of the exponential is. Because that's how we're going to undo the exponential, is take the log of the same base. The base of my exponential is 6. So I'm going to take a base 6 exponential, or sorry, a base 6 logarithm of both sides. Now again, when I'm writing these logs, the log and the argument are on the same level, on the same line. The base of my logarithm is a little bit lower, so make sure we're writing this correctly. And the way that this is read is log base 6 of 6 to the negative 2. So, back to this problem. My log base 6 and my 6 to a power undo each other, leaving negative 2 equals log base 6 of 1 over 36. And that's the equation that I want for an answer. Now we can hopefully move a little bit faster through this last one. We have 5 to the 1/3 equaling the cube root of 5. The exponential in this problem is the 5 to the 1/3 power, meaning the base of that exponential is base 5. So that means I take a base 5 logarithm of both sides. Again, the log and the argument are on the same line. The base is a little bit lower. The log base 5 and the 5 to a power undo one another, leaving the 1/3, and the right-hand side just stays put. And that's what we're looking for when we want to take an exponential equation and rewrite it as a logarithmic equation. The next things I want to explore in terms of logarithms are going to be about solving logarithmic equations. And we're going to look at solving logarithmic equations where the x is on the other side, where it's in the argument, and when it's in the base. And in the next lesson, we're going to get into when they're in the argument in a little more depth. Now, I do want to point out this first equation I'm going to look at isn't much of an equation anyhow. Let me point out what's going on here by looking at a completely different problem. This has nothing to do with this problem that we're looking at right now. But I'm going to give you a really difficult equation to solve. The equation is x equals 1 plus 3. Well, there's not really a whole lot to do in that equation. 1 plus 3 is 4. X must be 4. Woohoo! I'm a mathematician. All right. So what was going on there? X was on one side by itself. So the other side was nothing but calculation. So there was no actual algebra going on, it was just calculation. And so now if we look back at the actual example that we're working on, the x is by itself. So the other side is just calculation. So what I would do here is just do the calculation. We actually did problems like this earlier where we tried to say, let's rewrite this inside as 4 to a power, which would be negative 1 power. The log base 4 and the 4 to a power undo one another, leaving negative 1. So there wasn't any algebra in terms of moving stuff to the other side. You already had x equals, so it was just a matter of simplifying, in this case, the left-hand side. So that's what I wanted you to point out, here, is that when the variable's already by itself, don't worry about moving stuff from side to side. Just simplify the side that's nothing but calculation, it's nothing but numbers. To solve this equation where the x is in the argument, we want to go back to our definition of the logarithm, which was to take the base raised to the power of the opposite side equals the argument. So in this case, we would take the base, which is 5, raise it to the power of the opposite side, which is 3, and set that equal to the argument, which is x. Now 5 cubed is 125. X is 125. Simple as that. Now, we are going to look at slightly more complicated versions of this as we start to move forward, and especially in the next lesson. But the basic idea is always going to stay the same. That if we can have a single log by itself on one side, and the other side's a number, then we can get rid of the log. We can solve the log by taking the base, raised to the power of the opposite side, equals the argument. So we're going to say that over and over and over again to the point that you can probably say, hey, I should probably memorize that statement. We're going to take the base, raise the power of the opposite side, equals the argument. Now this last example about equations that we're looking at has the x in the base. Now we're still going to take the idea of base raised to the power of the opposite side equals the argument. But once we do that, how we solve it is a little bit different. So we just solve this resulting equation. This is a quadratic equation. We do have a perfect square on one side, number on the other. So technically what we should be doing is taking the positive and negative square root of both sides. Remember that was the square root property. which says x equals positive or negative 5. So we have answers of negative 5 and positive 5. But if you remember when we defined the logarithm, we had these two requirements that your base had to be positive and it couldn't be 1. Well, if we look back at our original problem here, x is the base, so we can't allow a number here that's negative or 0 or 1. So our negative 5 can't be allowed. So x equals 5 is actually the only solution to this particular equation. The next topic I want to get into in regards to the logarithm is going to be how to graph a logarithm. And I kind of already talked about this in a previous lesson when we were talking about graphing exponentials, because I had said if we can come up with a process to graph an exponential, then we can simply flip-flop x's and y's in order to graph a logarithm. And that's why we want to come up with a process for graphing exponentials. It's going to make graphing a logarithm that much easier. So let's consider and let's remember what we talked about when graphing exponentials. So if we had an exponential of the form f of x equals b to the x, then we had kind of a three-step process. The first step was to say the ordered pair 0, 1 is on this graph no matter what. And this came from the basic fact that anything to the 0 power equals 1. We then said if we move to the right, or we take a step to the right by 1, then we're going to multiply the y value by the base. And the idea of this was actually just the definition of what it means to be an exponent. Because what this is saying is as my x gets a little bit bigger, as my x gets 1 bigger, or in other words, as my exponent gets 1 bigger, by definition, that's multiplied by your base 1 more time. So that's what we're saying here, is that to get the y value, to do the calculation here, each time the exponent gets 1 bigger, the y value, or the calculation, we multiply by the base 1 more time. And then we say, well, we can kind of reverse that idea and say, if we reduce the exponent by 1, so if we move to the left by 1, then we're going to unmultiply by the base. We're going to multiply by the base 1 less time, or in other words, we're going to divide by the base. So that's the process that we had used for graphing exponentials. And with that process, we noticed that there was a horizontal asymptote of the x-axis of y equals 0. We never got down to a y value of 0, which also makes sense arithmetically. That if we think about taking a positive number, your base, and raising it to a bunch of powers, raising to a power means multiply by itself a bunch of times or divide by itself a bunch of times. So if we take a positive and divide by a positive, divide by a positive, divide by a positive, we're never going to get 0. We're never going to get negative. It's always positive. So we knew that we had this horizontal asymptote of y equals 0, or in other words, we kind of approached the line y equals 0. So what I want to do now is I want to talk about if I want to graph a logarithm, then let's just take every instance of x or y and flip-flop them. So if I take the exact same thing and say instead of graphing b to the x, let's look at the inverse. Let's graph log base b of x. Then instead of having the ordered pair 0, 1, we're going to have the ordered pair 1, 0. Instead of taking a step in the positive x direction meaning to the right, we're going to take a step in the positive y direction, which is up. And instead of multiplying the y value by the base, we'll multiply the x value by the base. Where previously we took a step to the left by 1, which was the negative x direction, now we'll take a step in the negative y direction, which is down. And instead of dividing the y value by the base, we're going to divide the x value by the base. Instead of having a horizontal asymptote, we'll have a vertical asymptote. And instead of that asymptote being y equals 0, it's going to be x equals 0. So literally, all we did is flip-flop the ideas of x's and y's, and this should give us a process for graphing the logarithm, and it does. Let's look at an example of how to use this in practice. So if we go through our 3 steps, our first step was to say the ordered pair 1, 0 is definitely on the graph. So let's start off by plotting that. Step 2 says if you take a step up, then multiply the x value by your base. So if I take a step up, that means I want to graph something on that horizontal line there. To figure out what value we get, we're going to take the old x value of 1 and multiply by our base, which is 2. So that means that my x value becomes 2. Now if I want to take another step up, so I want to graph something on that line there, then I'm going to take my old x value of 2, and I'm going to multiply by 2 again. That gets me 4. Take another step up. So now I'm on that horizontal line. Take my old x value of 4, multiply by my base again. That's 8. Now if I want to take another step up, I'd be all the way out at 16, which is off my graph. So I kind of have an idea of where this thing's going. But let's come back over here to this value 1, 0. Because then my third step says if you want to take a step down, then divide the x value by the base, which in this case, remember, our base is 2 for this problem. So if we go back to that highlighted value here and say, let's take a step down, then I'm trying to graph something on that line. My x value was previously 1. To divide by 2 means the same thing as to multiply by a half. 1 times a half is a half. So I'm going to get right there. If I want to take another step down, that would take me down to a y value of -2. I would take my previous x value of a half and multiply by a half again. That's going to get me 1/4. Now let's go ahead and go one more time. Let's take one more step down. My previous x value was at 1/4. I'm going to multiply by a half one more time to get 1/8. And hopefully what you're noticing now is we're going to get closer and closer and closer to the y-axis, but never touch it, because we're going to keep on taking half the x value, half the x value, half the x value. So my next x value would be 1/16th, then 1/32nd, then 1/64th, then 1/128th. It's just going to keep on getting closer and closer. And then as we go out here, it's really shallow. Because remember, our next x value would have been 16. So a logarithm takes a lot to get big. The y values don't get big very quickly. You gotta go really far out in the x. Let's go ahead and look at what this is going to look like if we have a fractional base. So step 1 was still the ordered pair 1, 0 is on it no matter what. Step 2 said if you want to take a step up, multiply the x value by your base. So our x value is 1. If I multiply by the base, which is a half, I'm going to get 1/2. And again, that was for a step up from here. So my x value becomes a half. Now suppose I want to take another step up. My previous x value was a half. If I'm going to multiply by my base again, I'm going to get 1/4. Then 1/8, then 1/16th. I'm going to keep on getting closer and closer and closer to that x-axis. So let's start talking about step 3. Let's come back to our original starting point and now say if I take a step down, let's divide the x value by our base b. So if I'm going to divide by my base of 1/2, that's going to mean the same thing as multiplying by 2. So if I want to take a step down 1 from that 1, 0, then my x value of 1 turns into an x value of 2. If I want to take another step down, then I'm going to multiply by 2 again to get 4. Another step down to get 8. And now we got a basic idea of what this thing looks like. So similar to the exponential, when our base was a fraction between 0 and 1, our graph was decreasing, meaning as you walk left to right, you're going downhill. And like with the exponential, when your base was larger than 1, you're increasing, meaning as you walk left to right, you're going uphill. That would be something I might write down, especially for your final exam, that for both the exponential and the logarithm, if your base is bigger than 1, as you walk left to right, you're going uphill, you're increasing. And for both the exponential and the logarithm, when your base is between 0 and 1, then you're decreasing. As you walk left to right, you're going downhill. So now we're going to shift gears to talk about the rules that go along with logarithms. So what properties do they have? What rules can we do? What things can we do? So really all we're going to do here is we're going to say, well, what were your rules of exponents? And let's just do the same thing, only flip-flop x's and y's. So that's exactly what we want to do is we want to say, all right, our exponential function was the function f of x equals b to the x. So b to the x being the function part there. That's the exponential. And so we have this rule for exponents that says when I'm multiplying together these two exponential functions, the result is an exponential function where I added the arguments. So that's where I have this written out in words. So that rule that we all know, b to the m times b to the n equals b to the m plus n, as long as those bases are the same, we can say that as when I multiply the functions, so I have these exponential functions, the result is to add the arguments. Now when you look at that, I want you to notice the word function, well, your function value is your y value. Your argument, or what you're plugging into the function, that's your x value. So really, if we want to talk about logarithms, just flip-flop those two words. When you multiply the arguments together for logarithms, the result is to add the functions. And that gets us our first rule of logarithms, which is log base b of a product, m times n, can be written as a sum of two logarithms, log base b of m plus log base b of n. This is a rule we're going to use a lot, so you definitely want to make sure you have this memorized. But the reason that it's true is simply because logarithms and exponentials are inverses of one another. There's no real proof necessary. All we have to do is flip-flop x's and y's. So I do want to point out, with this rule that we just wrote that said, oops, let me not use a capital there, it's not appropriate. We had this rule, log base b of m times n equals log base b of m plus log base b of n. I want to point out with this rule, just like any other rule in math, it can go either way. So we are going to have times that we go left to right, that we start off with a single log and we write it as a sum of logarithms. And there are times that we're going to go right to left, that we're going to have a sum that we're going to rewrite as a single logarithm. And so these directions here indicate that we want to write this as a single logarithm, so we're doing the right to left direction. We're saying I have two logs of the same base, that I'm adding together. So I could write that as a single logarithm by multiplying their arguments together. Now, 10 times 3 is 30, and that's my single logarithm that I was looking for. As I move on to this next one that has a fraction, basically the same game plan. We're going to say they're both base 3 logs. That's important. So instead of adding 2 separate logs, I can make a single log by multiplying their arguments. Then we'll actually multiply a half times 12 to get 6. And we can do this with variables as well. So these are both base 2 logarithms. So we could multiply x and x plus 2 together. And we could distribute the x across, giving us x squared plus 2x. Now where this is eventually going to be going, so think next lesson, we're going to be able to solve logarithmic equations that start off with multiple logarithms. Because we can use these properties to combine them to a single log, and earlier in this lesson, we talked about how to take a single log and solve an equation by taking the base raised to the power of the opposite side equals the argument. So that's where we're going with this eventually. So let's talk about a second rule. Now we had a quotient property for exponentials that said when I had b to the m divided by b to the n, I could subtract the exponents. So if we kind of want to do the same things we did before and turn this into words, we can turn this into words by saying that when you're dividing the functions, the result is to subtract the arguments. That's what's happening there. And then we can again say functions or function values are the y values. Arguments are the x values. So if I want to make a statement about logarithms, I flip-flop those two things. And then I say when I'm dividing the argument, the result is to subtract the function. That gets me another rule. If I have log base b of m over n, I can rewrite that as a subtraction problem of log base b of m minus log base b of n. And it's important that we get this in the right order. Since subtraction, it definitely matters. That you should notice that this is top, this is what was originally on the bottom. So make sure you do have those in the right order. Obviously, that's really important when we're dealing with subtraction. So our directions are, again, write each of the following as a single logarithm. So it's similar to our previous example, only this time the rule that's going to come into play most frequently is log base b of m over n, giving us log base b of the top minus log base b of the bottom. And again, like the last one, we will have situations that we work left to right. We'll actually see it later in this lesson. But in this case, we're going to be going right to left. So we're going to start off with a difference of logarithms that we rewrite as a single logarithm. And so in doing so, it's important to get this in the right order. That the first thing, the thing to the left of the subtraction sign, is what goes on top. And the second thing is what goes in the bottom. And then we can actually do that division. 27 divided by 3 is 9. And there's our single logarithm. Now we can involve variables as well in this next one. They're both base 5. We put the 8 in the top. We put the x in the bottom. And this time there's nothing to simplify then. Nothing divides out. That's as good as we can get. And we can even try to get more complicated with some quadratic looking arguments. But really the same thing is going to happen. The first guy goes in the top. The second guy goes in the bottom. Now, if that fraction simplified, we would definitely want to do that. But remember, in order to do that, we would need to factor the top and factor the bottom. Neither the top nor the bottom factor in this case, so this is really as good as we can get. So we have one more rule that I want to talk about in this lesson. And this one doesn't necessarily come directly from an exponential function rule, but really it comes from the definition of what an exponent is, though. So do remember our first rule. So our first rule that we came up with so far was that if I have log base b of m times n, that I can turn that into a sum of logarithms. So what I want to do now is I want to try to come up with a rule for when I have m to a power inside my logarithm. So what I want to do first with this to figure out what the rule is, so keep in mind that's what's going on here, so we're trying to figure out what the rule is I want to just use the definition of what an exponent means. This means m times m times m a bunch of times. How many times? R times. So that's what's going on. That's what it means when I have log base b of m to the r. Well, let's look back at our rule that we previously had. We had this rule that if you're multiplying things inside the argument, you could write that as a sum of logarithms. So I could actually rewrite this as log base b of m plus log base b of m a whole bunch of times. How many times? R times. But log base b of m, log base b of m, log base b of m, I'm adding the same thing to itself a bunch of times. That's the definition of multiplication. If I add x plus x plus x, that's 3x. That's the definition of multiplication. If I have x squared plus x squared plus x squared, that's 3x squared. It's the definition of multiplication. So if I'm adding log base b of m to itself a bunch of times, then by the definition of multiplication, I'm going to have something times it. That something being how many times I added it together with itself. Well, how many times did I add it with itself? R times. So this is actually our rule. Our rule says if you have log base b of m to some power r, then basically what this is saying is you can bring that power down in front as a coefficient. Now, just like with the other rules, we could go either direction. So what I mean by this is if you have a coefficient in front of your logarithm, you could bring that coefficient up as a power if you really wanted to, if there's a need to. And we're going to look at situations where there is a need to. Or the other direction, the other direction with this is if you've got this exponent up there and you don't want an exponent, you can bring it down in front as a coefficient. And that's what this last rule is going to be, this power rule. And let's see it in action. So for this first example that we're asked to use the power property to rewrite the expression, we're just going to take the exponent and bring it down in front. That's all we're going to do to say it's 3 log base 5 of x. Simple as that. Done. That's all this power property is telling us. Now, as we look at the second example, we're asked to do the exact same thing. But on first glance, I don't see a power. But this is where we got to remember, this is important for really this entire lesson and really this entire unit, is to remember that radicals are powers. Since we like dealing with powers in this lesson here, let's rewrite that radical as a power. So let's rewrite the 4th root of x as x to the 1/4 power. At which point, applying our rule should be pretty easy. We're going to take that power of 1/4 and just bring it in front as a coefficient. And that's all we're doing right now. All right, so now let's look at some examples where we have to use multiple rules in the same problem. So our directions are the same directions that we've seen previously to write the following expression as a single logarithm. So our goal is to end up with the letters log only once. That's our goal. We're looking for a single logarithm. So on this first example we're looking at, one of the things I want to point out is that we cannot use the rule log base b of m plus log base b of n. We can't use that rule because we don't have single log plus single log. What's throwing us off are the coefficients 2 and 3 here. So we have to handle those coefficients first. So as far as the order that we do things in, that should jump out and say, you know what, I got to get rid of that coefficient, and that's where we're going to use the newest rule that we came up with that says I can take that coefficient up as a power. And I'm going to do the same thing in this second log, is I'm going to take that 3 up as a power. 3 squared is 9, 2 cubed is 8. Now I can use that rule that says when I'm adding two logarithms together, I can write a single logarithm by multiplying their arguments. 9 times 8 is 72. Now, just a reminder, I know I mentioned this earlier in the lesson, but it's a big pet peeve of mine that we write these properly. The letters log and the argument 72 are on the same line on your lined paper. The 5 for the base is a subscript, it's a little bit lower. Let's look at the second part of this example. For the second part, again, you're seeing a coefficient here. We got to handle the coefficients first. You can't use your sum or difference, or if you want to call it your product or quotient rule, we can't use those if we have coefficients in front. So the first thing we got to do is to take that coefficient of 3 and bring it up as a power. Now that we're taking the difference of two logarithms, we can make a single logarithm by making this into a division problem. The x cubed goes on the top, the x plus 1 goes in the bottom. Nothing simplifies there. That's as good as we can get. Now we have 3 logarithms in this last piece. What you want to look at is the fact that these guys are positive. We're going to multiply their arguments, or in other words, they'll be in the top. This last guy that we have a subtraction sign with, we're going to divide by that argument, or in other words, that argument goes in the bottom. So that's something I want you to think about as you look at this guy, because then we can just say it's log base 4. Up top I have 25 times 3. In the bottom I have a 5. And then I can start simplifying stuff. I can say that's 75 over 5. 75 over 5 is 15. Okay, so let's go ahead and read these directions. Write the following expressions as sums or differences of multiples of logarithms. Now, one of the things I really want to pay attention to as I read through this is that word multiples. So it doesn't just say multiple logarithms. It does say multiples of logarithms. A multiple of 5, let's say, is 5, 10, 15, 20, 25, 30. It's 5 times something. So in other words, we want to multiply our logarithms by something. Or in other words, we want coefficients. So that's the clue that says we want coefficients. Now, in addition, we do want to rewrite this with addition and subtraction of various logarithms. So for this first example, we'd rewrite this as log base 3 of 5 plus log base 3 of 7. Because of the fact that we were multiplying inside the argument, we rewrite this as adding logarithms. We're going the other direction on the rule. So I'm not done with this one yet. I'm just taking a quick aside. So remember that rule was log base b of m times n equals log base b of m plus log base b of n. Previously, when we were writing single logarithms, we were going right to left. So what we're doing differently now is now that we want multiples of logarithms, we're going left to right. Now also we had that 4 in the bottom, which means we subtract him. Now if that whole multiples of logarithms thing wasn't there, we'd be good with this answer. But notice that 4 could be rewritten as 2 squared, meaning I could bring that 2 down in front as a coefficient. So because we wanted coefficients, whenever possible at least, that's how we're going to write this problem out. Now we can do the same thing when it comes to variables. Now one thing I do want to point out is that we cannot bring the 5 down in front right now because your entire argument is not being raised to the 5th power. What we do have in our argument right now, though, is division. So we can rewrite this as a subtraction of 2 logarithms. And now we can say, oh, now I have an exponent, that my argument's being raised to an exponent. So now I can bring the 5 in front of his logarithm, and I can bring the 2 in front of his logarithm. And now I've achieved my goal of writing sums or differences of multiples of logarithms. And again, the multiples meaning we like coefficients. The last type of example that we're going to want to look at are going to be problems that give you a base of b. You don't know what the base is. And you're going to be asked to approximate these values based on some other given values. So in this case, we're given what log base b of 2 is. We're given what log base b of 3 is. And we're asked for each of those 3 to calculate a value for them. Now we can't just simply put this into our calculator because we don't know what the base is. So when we're approaching the problem like this, your game plan is going to be to rewrite the unknown argument using the known arguments. And the way you want to rewrite this is think about the 3 rules we have. Product rule, quotient rule, and power rule. You're going to think about how could I rewrite that argument using multiplication, using division, or taking one of my known arguments and raising to a power. Then you're going to use your rules of logs to rewrite the original problem using the known arguments only. Then we can substitute the known values in that were given to us in the directions. So let's go back to that example and see if we can do those problems now. So the first problem we're going to look at is log base b of 81. So we want to look at 81 and we want to look at the known arguments of 2 or 3 and say, can I multiply 2 and 3 to equal 81? Can I divide 2 divided by 3 to get 81? Can I take 2 to some power to equal 81? Can I take 3 to some power to equal 81? And of those, yes, I could take 3 to some power to equal 81. And so that's my game plan on this problem. The first thing I'm going to do is rewrite that 81 as 3 to the 4th power. That's step 1. Rewrite it. Step 2 is to use the property of logs that applies. I cannot plug in this value yet because I don't have log base b of 3. I still have log base b of 81. But if I use that property of logs that says, go ahead and put that exponent in front, as a coefficient. Now all of a sudden, I have log base b of 3 right here. I know that log base b of 3 means the same thing as 0.68. So that means I can rewrite this as 0.68. Now is when I can get my calculator involved and say 4 times 0.68. Oops, I didn't say times, I did a dot there. Let me try that again. 4 times 0.68 is 2.72. And that's my answer to that particular problem. So as I look at my second example, I again want to say, is it 2 times 3, 2 divided by 3, 2 to a power, or 3 to a power to get 6? And hopefully it's clear that, yeah, the 2 times works really well here. So I'm going to start off by rewriting this as 2 times 3. Now again, I can't do a substitution yet because I don't have log base b of 2 and I don't have log base b of 3. I have log base b of 2 times 3. So I need to use a property of logs to rewrite this as log base b of 2 plus log base b of 3. Now I can do a substitution. Log base b of 2 is 0.43. Log base b of 3 is 0.68. And now I can bring my calculator into the mix. So now I can say 0.43 plus 0.68. When I add those together, I get 1.11. And that's my answer to that problem. So again, if you don't use a property of logs, you didn't do this problem right. You have to use a property of logs to get down to an answer here. Now for this last one, there's a 2 involved, but there's also a square root. But if we go back, I talked about this for advice earlier. Anytime we have a radical, try to rewrite that radical as a power. Since this whole logarithm business is all about undoing powers, it makes sense to rewrite that square root as the 1/2 power. Now we can use that power rule to bring that 1/2 out in front. And then we can do the substitution that log base b of 2 was 0.43, half of which is 0.215. And so that's the answer for log base b of square root 2, given those initial values that we have.